Welcome to today's Manufacturing Engineering Media webinar. Our topic is improving efficiency through software and automation. Hello, I'm Pat Wozniak, Senior Editor at ME Media. My beat includes covering developments in manufacturing software, CNC controls, and automation technology. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsors are CamWorks, Carl Zeiss Industrial Metrology, CG Tech, Simco Integration, Delcam, GibbsCam, and SolidCam. During this webinar, you will learn about how software and automation affects all aspects of the manufacturing world. You will be able to ask questions during the presentation using the Q&A box that will appear on the right side of the screen. Following our presentation, our presenter, Thomas Kerfis, will answer your questions. If time runs out before we can get to all the questions, we will make sure the answers are emailed to you. Portions of this webinar are pre-recorded. As often happens with viewing videos over the internet, the quality of the presentation can be affected by the type of internet connection you have, the amount of total bandwidth available to you, and the number of people accessing that bandwidth at that time. If you experience difficulty, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at pwozniak@sme.org. Thomas Kerfis, our presenter, is Professor and Husco Ramirez Distinguished Chair in Fluid Power and Motion Control at the George W. Woodruff School of Mechanical Engineering at Georgia Institute of Technology. Educated at MIT, Kerfis has taught at Carnegie Mellon University, Georgia Tech, and Clemson University. In 2012, he returned to Georgia Tech, and during 2012 to 2013, he was on leave serving as the Assistant Director for Advanced Manufacturing at the Office of Science and Technology Policy in the Executive Office of the President of the United States of America. He currently serves on the Board of Directors at SME, the National Center for Defense Manufacturing and Machining, and the National Center for Manufacturing Sciences. Now, here is Thomas Kerfis.
Thank you, Pat. I appreciate the introduction, and welcome to this webinar on improving efficiency through software and automation. I also appreciate that everybody is online here to listen to this webinar. I think we have some good information to put forward to you. Certainly, we're not going to cover every specific detail in this area, but really the idea is to get you thinking about where we're at and where we're going. So in terms of today's talk, I'm going to start off a little bit with saying, look, here is what manufacturing is and why it's important to our economy. I mean, I think, again, I'm preaching to the choir, but I think it'll be good just to, at least make you feel good about the area that you're in, which you should feel good about. Then we'll talk about some of the design and manufacturing tools. So, what's going on with some of the CAD/CAM systems and where are they going and what kind of capabilities are we seeing and how are they being utilized, moving off into robotics and automation, which of course we see that this is a great opportunity for us to really leverage what's going on here in the United States in terms of capability, infrastructure, and so forth, to use this automation, rather than trying and compete with what we would say would be low-cost labor, perhaps, and in particular, I think working on jobs that people really don't want to have, in production operations. I think it's worthwhile to talk a little about additive manufacturing, what's going on there and where that's going and how that fits into the big picture, and then kind of going off to the cloud, and I don't know whether you want to call it the silver or the gold lining, but basically, where's the value there? And we'll close up with digital manufacturing, so a little bit bigger picture there, and then talk a little bit about some of the cold realities, hey, this is what the future is going to bring us and what we have to be careful of, so forth. So, again, in terms of manufacturing, why does manufacturing matter? Basically, if you take a look at it, 70% of the United States research and development is related to manufacturing. Manufacturing conducts that, and 90% of the patents issued in the U.S. are related to manufacturing, or are linked into manufacturing. And I think that should make a lot of sense to us because basically, if you get a patent, you want to be able to make, it, and so the patents really, the patents are a way of protecting your ideas, but manufacturing gets those ideas out to allow you to make a profit on them. And I think that, again, I know I'm preaching to the choir, but it's been proven time and time again that there is a very close connection between research and development, design, and manufacturing. So it's really this, what we would call the industrial commons, the know-how, hey, I want to design this. Well, this is, you're going to design a product and think about how you're going to make it all at the same time. If you can make the product, you have a pretty good idea, about what the product is all about. The other thing I think that is very important is manufacturing is a significant economic multiplier. So for every dollar of manufacturing output, the economy realizes another $1.40 of growth or expenditures. So for every dollar that is put out in a factory, in the service sector, and over in the shopping malls and the grocery and whatever, you name it, that is generating another $1.40 for our economy. So it's really important. It's a great multiplying factor for the economy. In fact, it is the number one multiplying factor in terms of our economy. And of course, last on the list is that it is critical for national security. So again, you can imagine that we do make a lot of different products here in the United States, and it is good not only economically to be making them here, but it's also good not to be relying on other parts of the world to be making a lot of these products. Certainly there are products that are made in other parts of the world that are imported here, but there are other elements where, again, you could imagine, sure, bearings are made here, they're made abroad and so forth, but if we didn't make bearings, how life would change dramatically if all of a sudden we couldn't get a hold of bearings. So these are types of things that are important, and why manufacturing is important to us here in the United States. So let's take a look at sort of the big picture. Where and I'm borrowing this from the federal government, but really where things are going. There are a lot of different efforts going on in the federal government. I think people might have heard about the National Network for Manufacturing Innovation. This is trying to take technology that is being developed in research and development groups, whether at universities or in industry or small enterprises and so forth, and getting that innovation out and really scaling it up quickly, and not only scaling it up for the big players, but also for the small and medium-sized manufacturers, the so-called SMM. So to really get some of this technology and capability out to everybody so that we can get new products out into the market quickly. Another one actually is Materials Genome Initiative. So this is basically developing new materials in half the time. Robotics is another one. We'll talk a little bit about that down the road, but basically how do we leverage robotics in this particular case, of course, in manufacturing, and a lot of other areas as well. Additive manufacturing is another one we'll hit on, but this is the whole 3D printing is part of additive manufacturing. And then we will also hit on the big data issues. That is to say, look, we have a lot of data being generated in our production operations, for example. It could also be, certainly if you look at air traffic control or transportation, in terms of, traffic control and things like that. You have a lot of data out there. How can we use those data sets to improve our lives, to help work out better ways to execute various missions, or just to make lives easier on people. But if you look at it, this figure over on the right, really, and I borrowed this from the Materials Genome Initiative, but the idea really is, look, on the outside you have some big, important concepts: human welfare, clean energy, our next generation workforce, national security. So these are the things that all of these different efforts are trying to achieve, in sort of the grand scheme of things. And then, you insert there, so like I said, I borrowed this from the Materials Genome Initiative, so it's Material Innovation Infrastructure. So that's what we're looking at in this particular figure. But what I want to draw your attention to are those three little circles, those little kernels in the middle, and there's some overlap. And the idea really is, there are there are some computational tools. So we've got all sorts of great high-performance computing. They call it HPC, supercomputing, whatever you want to call it. We've got these great analytic tools, finite element analysis, and so forth. And so we've got this computational capability that we use to really model our experiments, right? So the idea really is if we can run an experiment, we can simulate that experiment in our computational tool, then we have a pretty good model. And now, I'll just pick on the automotive sector, right? So we do use the crash wall, but we have better and better models, and so we're using the crash wall less and less nowadays. And if you don't have to crash a vehicle in testing and you can simulate it, number one, it's significantly less expensive, and number two, you can really do a lot of design iterations much more rapidly than setting up the whole experiment and crashing it. But when you do crash it, you do generate data. So if you take a look at the experimental tools, yes, we generate data, and those can actually be fed back into our computational model. So these three things really come together to form really a nice trio. And whether we're talking about CAD, CAM, or robotics or whatever, these are the types of things we're looking at. So we're going to have some hardware, some experimental capability, some real-world systems. We're going to have some simulation, and those are going to be linked together by the models that we're using as well as the data that come out of the experimental tools to run the computational tools. And by the way, it works the other way around, where the computational tools may generate data that tell us where to look, or what experiments to run to get a better understanding of things. So let's take a look at some of the CAD-CAM systems, computer-aided design, computer-aided manufacturing, or sometimes also known as CAE, computer-aided engineering. With our higher performance computing nowadays, not only are we drawing geometry, so here's a connection, or a part on a motorcycle, and you see that part there underneath the motorcycle, but very quickly we can do things like finite element analysis, and we can find out where the higher stress concentrations might be. So the orange area, orange-red area in there, that's where we're going to have higher stresses, so we may turn around and say, well, we have to add more material there. The blue area, well, we don't need as much material there because there's not as much stress on there. And in fact, our designers now can start to design these parts, integrate them into systems, and in real time start to get a feel for, well, what does the stress look like, So when you start to talk about things like safety factors, I know when I was a student, we'd say, well, a safety factor of 2, that should be good. Now you can actually go and say, well, what is the load that this particular part will see on the motorcycle? And that load, it may come from simulation, but it also, probably will come from experimental analysis. So we've got some simulation perhaps going on, but certainly some experimental work going on, so we know what the loads look like. And now we can turn around and say, okay, we want to make sure that we have a safety factor of 2, and yeah, but we don't need to double the thickness of the entire part. Just down in that red area, we need to make it a little bit more thick so that we can handle twice the load that we're anticipating seeing in the worst case scenario. So this really brings some power to the designer. The other thing it does is it brings a little bit more reality to the designer as opposed to just a factor of 2. Now you can say, yes, I know what my maximum load is, and I'm designed for twice that maximum load. So, and of course, and I have already mentioned the crash wall, and it's not just, designing for load and so forth, and the finite element analysis tools and so forth, but we can actually even look at some of the dynamic types of systems. And here, of course, you're seeing the crash wall. You're seeing how the vehicle is failing. You can determine, where the stresses are. You can even look inside the cockpit and understand what's happening to the occupants and so forth. And again, running this simulation on your computer, which happens very quickly, is significantly more economic than crashing the vehicle. And again, as I said before, we probably will never get rid of that crash wall, but we can sure minimize the number of times we use the crash wall. So not only does it help us in terms of design, but it also helps us in terms of rapidly iterating on our designs. And in many instances, let's say a new standard comes along. You want to know how that new standard is going to affect your design, or if your design is going to be able to handle the new standard. Let's say the new standard for a crash might be a higher speed impact. You can simulate it very quickly and understand if you're close, if you're far, what you might need to be doing. But even beyond that, as we look at this, here, now we're looking at an aircraft at a fuselage, at a cross-section of a fuselage. You might even look at some of the design trade-offs, on the economy. So if you look at this, the upper section of this fuselage is where you put your passengers. The lower section is where you might put your cargo. And what you can do is you could say, well, maybe I can move, my floor up a little bit and give myself a little bit more cargo space. And if that happens, how does that affect the performance of my aircraft, of my fuselage? Maybe I need to move it down a little bit. Maybe I need, some stiffer, ribs, around the outside. But you have the opportunity to really take a look at functional, the functional capability of your design, as it relates to, will this particular one perform, and what are the trade-offs? So it allows the designer to take a look at these types of trade-offs. And by the way, what's coming up next, of course, is the designer will move things up and down and say, okay, well, here's sort of the optimal trade-off between cargo and space for people, for example. And by the way, the space for people, you could fit people in there and move that floor way up, but then they're cramped and so forth. And there are some human factors and ergonomics that go in there, and you can start to tie all of these together. And now, in fact, we probably know that it's going to be some type of optimization. So there's going to be some iteration. Whether a person does it or whether the actual computer does this iteration, really moves towards, doing some optimal design to say, yes, this is what I'd like to get. Here are my different trade-offs. Go give me a recommendation. And again, you're iterating back and forth. Give me a recommendation as to where I need to be. So a lot of good capabilities there and so forth in terms of, how you can move things forward, what you can do there. And just to sort of go back to this whole, concept of modeling the process and so forth, this particular run, I believe this is an image of a couple of different levels of a blade for a wind turbine. And what's very exciting about this is, our models now are also starting to come back to how the product is built. So this is no longer just a solid piece of material, right? This is a composite material, but what you can see now is you can even model the layers. And in fact, even in terms of the layers, we know that the composites, they could have, if it's sort of a continuous fiber composite, you've got significant strength in the direction in which the fibers go. So in fact, we can incorporate not only the layers, but we can incorporate even the directional strength. So instead of, say, well, it's like a block of steel, it's pretty much, homogeneous in terms of its strength. It doesn't matter, which direction you're pulling on it. Now we can start to take a look at, well, no, how should we design this and how should we manufacture this so that we get the optimal strength, in our part, and that strength is going to be directional. The other thing that I really like about this particular one is that you see some of the meshing on there, and you can see that, in certain elements, and we know this in terms of finite element, that the meshing is going to change depending on, where stress concentrations are and so forth, where you want to get higher resolution. And a lot of that in the past in finite element has really been done manually, has been done, it's almost like, an art form, hey, I know exactly where I need to go here and so forth. And a lot of that meshing capability is now being handled automatically. So, that's not to say that everything is going to be handled automatically, but a lot of the details in the analysis packages and so forth in your design, you're going to be freeing your designers to think at a little bit higher level, than I've got to remesh this, and then what should my meshing be, and what should my spacing be, and how do I split this meshing up and so forth. A lot of that is now going to be handled, and it is already being handled automatically, and it's getting better and better over time. So this also allows us to think, in terms of very high level. So it allows us to abstract out and do some really nice design work. And then, of course, you can turn back around and say, not only can we design it, let's start linking it into our CAM systems. How are we going to make it? Where are our high tolerance areas? Where are our clearances? How does it, move forward? It was interesting. I was talking with our chief technician here in mechanical engineering at Georgia Tech, and he told me that the kids nowadays, it used to be 20 years ago, you brought a piece of paper with a drawing on it and say, well, I want to make this. And then he would sit down with the student and say, well, you can't actually do this and that, and, you've got to align this, and, and then would work on making the product. What the students do now is they actually draw their product up, They run a bunch of analyses, including finite element. They run a manufacturability analysis. Yeah, I can make it on this, for example, 3-axis mill. And then they actually generate the G code, with our CAM products, that generates, that will be run on the machine. So instead of bringing a piece of paper to our chief technician or our chief machinist, they actually bring a memory stick, to him. And there are still some things that he has to work on with it, but, we have to recognize that these tools are also starting to generate a different generation of machinist, of technician, of engineer. They think differently. They work differently. Their output product is different. It's no longer a piece of paper with a drawing on it. It's now, in some instances, even G code. It's been post-processed. And so one of the things that a lot of what's going on, in the CAE area, is that's happening is we need to make sure we understand what our next generation of capability is and how to leverage it, right? And not to sort of go back, well, let's draw it on a piece of paper. We wouldn't do that anymore, right? And so how do we move this forward, and how do we make use of these tools? And even to the level, of representing some of the most complex systems. So, here you've got a turbine, right? This is a propulsion unit. You've got all sorts of dynamics going on. You've got complicated geometry. You've got thermal analyses, et cetera, et cetera, et cetera. But the beauty of this is you can go back, and again, you can look at it at a very high level, and you can understand it from a systems perspective, and even drill down and understand, well, how am I going to make each one of these blades? What are the feeds and speeds? What is the tooling necessary? So if you need to drill down, you can, and that's going to require some more expertise. But again, if you need to step back and say, well, gosh, if instead of using, a 3/8-inch ball mill, for machining this, if I used a 1/4 inch, how is that going to help me in terms of my final product? Or even, in fact, actually, we know that we would mill these out and then we would polish them up and so forth. What might I save on some of the polishing time and things like that? And how is that going to change the performance of my product? So the tools allow you to drill down into some very specific capabilities, but they also allow you to step back and really understand these complex systems at a very high level, which is quite exciting. So now what I'd like to do is shift a little bit more towards, some of the capabilities that we're seeing on the, on the machining side, and to talk even a little bit about, some upgrades or some updates that are coming where it's not going to be particularly costly, to do this. And again, we see a lot of this, and we'll talk about this on the data side, but there's a lot of capability out there that we really haven't even begun to leverage. And so let me just give you an example here. This is a bore. Well, we've got a steel piece over there. I think that piece is probably 50-100 steel. And we normally would do this in a bore grinder, but we can't show it to you for proprietary reasons, blah, blah, blah. But you've got this thing, and we're spinning this part, and you might recognize the sensor we have there. It's a Marpos through bar. It's a bore grind, it's a bore gauge. And basically what it's been used for in the past is to say, okay, when have we hit our target size in a bore grinding operation, typically a shoe centerless, bore grinding operation. And, one of the things that we looked at is we said, gosh, well, we're getting position information now. We don't need to just get size out. I mean, what else can we do? And, in fact, we looked at actually tracking the position, the bore size, as it was being ground in real time. And, in fact, the reading that we get, looks something like this. And there are two fingers in there, one at either side of the ID. And we saw a readout like this that we're getting in real time. Well, guess what? This looks exactly like, a roundness measurement. And in fact, what we did is we said, yeah, we can actually take the data coming off of this bore gauge and get a roundness measurement. And it was done. And it was a matter of a little bit of software. So the hardware was there, and it was just the data were available. We just had to capture that data, move it, into a computer and so forth. And in fact, not only were we getting roundness information, but we were even doing things like computing Fourier analyses on this and so forth, which is exactly what you would be doing on your roundness machine. And in this particular case, we found 31 undulations per evolution in high-frequency chatter, but we were doing it during the grinding operation. So in fact, we could pick out if we were getting high-frequency chatter, we could control that shatter, and then we could also provide for every part made, inspection information if it was deemed necessary. And again, this is all making use of technology that's been out in the field for quite some time, but just capturing the data. So these are the types of things that we're going to be seeing in terms of where we're going. It's not only, wow, new and cool tools, but we've got some great tools, like that gauge. We've got some great tools that are already out there, and how are we going to use them, in terms of next-generation capabilities? And those next-generation capabilities, if you look at it, your machine tools, they are online. You're downloading, typically G-code to a lot of the CNC controllers today. And so, a lot of this information will be moving back and forth. Sometimes, you'll have enough computing power on your machine tool to actually make use of the data. Other times, those data sets will be shipped up to other computing areas. They may be within a plant. They may be even at a different location, for processing. And as you get a new machine tool, you may reprogram things because the new machine tool has more processing power on it. But it's really going to be making use of the processing. And again, I really liken this type of concept to our cell phones. So first of all, how much of a phone is your cell phone, right? How often do you use it as a phone as opposed to anything else? But we still call it a cell phone. But if you told me 20 years ago, I'll give you this great iPhone or Android or whatever, that has all sorts of great capabilities on it, and I'll just give it to you for free or for $100 if you sign up for a 2-year plan, you would have thought I was nuts. Where is that coming from? And yet today, that's pretty much the norm. And I think that's what we're going to see down the road. Hey, I've got this software package that we can put on your machine tool, and you've got these types of sensors. Maybe it's a MARPOS sensor, and you'll be able to get lots more information out of this in terms of your, process capabilities and so forth. And again, we keep moving along those lines. We see things like, in-process machine tool metrology. So integrating that metrology, right into the machine, right? And doing things like machining characterization. So, is this a good part? Is it not? How do we go about characterizing the actual machine itself? Error mapping the machine. So, as the machine wears out, we might go back and we might, remap the machine. Now, of course, we all know there are two really big issues with this machine tool metrology. Number one is if there's an error in the machine itself, a geometric error, let's say, in the way of the machine, you're not going to pick up on it because you have the same geometric error in your metrology system, so you don't have a separate metrology frame. That's part of it, but we can take care of mapping that out and making sure that your frame is okay, or at least it's mapped out appropriately. The other big issue that we'll be looking at, is, well, gosh, is it worthwhile to probe in the machine? Because while I'm probing, I'm not making parts. I'm not making chips, and so that's going to cost me. So how do I move that forward, and how do I how do I understand that value? And again, that's not really what I would say. That there's some analysis at the machine tool level, but a lot of these capabilities are actually going to a higher level and looking at cell performance or line performance or actually production, at plant performance and so forth. So again, a lot of data out there, a lot of controlling of different variables. And in fact, in this particular case, yes, we're measuring geometry, but we're also looking at measuring subsurface damage. How do you control any kind of cracking, or overheating in the part? Because on this particular, airfoil, if you machine it too hard, you can actually generate some cracks in the part, which would actually cause failure, during operation. So we're looking at controlling parameters all the way down from individual machine tools all the way through production operations. And by the way, if I've measured this, and this is a roughing operation, I can provide that roughing information to my finishing machine, so that I don't have, so that I can servo, I can, GOO, I can wrap it closer into the finished surface without worrying about crashing my machine. That's going to save on time as well. So there are a lot of different things, that we will be able to do, and in the future by just taking our quality information, our machining information, from, and in many instances, from sensors that are already out there, and really leveraging it. So let's shift gears now, and talk about, I just put this slide up really quickly, in terms of the National Robotics Initiative, and there are lots of different application spaces. And so we talk about manufacturing, and we're going to focus on that. But we really do in terms of, intelligent transportation. So we hear about the Google car and it's going to drive itself and so forth. Well, I tell you this, you're going to have AGVs, and right now you've got to put the strip down on the floor, or somehow you've got to navigate it. The AGVs are going to navigate themselves, in vastly different, approaches in the future, which will give us significantly more, types of capabilities. But a lot of the, we see manufacturing automation, but I mean, a lot of this, we're really drawing on, on different types of, different work that's going on there in the robotics area. And I thought, let's just take a look at a couple of different video clips, that sort of show us, different opportunities and so forth. So let's see, the first one, actually, this is from a colleague of mine, Vijay Kumar, and this is the so-called, drones, right? These are little quad rotors and so forth. Now imagine, if these were making, tooling deliveries and so forth within your plant, they could move around. They're not limited by, where they can go on the floor. They can, in fact, go over, places. They can go through places, through doorways. They can go up over beams, and so you don't even worry about, where people are and so forth, but you can get your tooling delivered and so forth. And you don't even worry about them crashing, I mean, they can actually do some great stuff in terms of control, and so forth along those lines. And again, people think, well, gee, does this really make sense? Does it not make sense and so forth? Is it that far out? I tell you, it's not particularly far out, and here's actually a video of them actually doing a little bit of assembly. So what now, as opposed to having a fixed robot, what if you could move some of the smaller pieces, like these guys are moving here, off into your assembly line to get some assembly work done? It can be done. Now, the design here, what you see, these are magnetic interfaces, so yeah, the quad rotors are moving in, and as they go down, they sort of lock into, into the magnetic interface. But and as we've already seen with a lot of the design for assembly, chamfering, and things like that, it is not that far out to say, yeah, we could be doing some of this type of work, with these types of quad rotors, and they give us tremendous flexibility. Again, maybe that's a little bit far out, but I wouldn't, put it past, seeing some of these things, happening, in the next, several years. Certainly at home, we're already seeing vacuum cleaners running around our house, cleaning our house, and so forth. So, some of the other things that we would look at, is actually even material transport. Why even think about, rolling things around on wheels? This is the Big Dog out of Boston Dynamics. Now, this was developed for the military, and the idea here is, the warfighter moves around, out in the field, and Big Dog doesn't track right behind them, but Big Dog eventually finds them and brings them all of his heavy material. This is certainly a possibility, and we see a lot of times, where AGVs are limited is because they can't, they don't have access. So maybe this material is a little bit too heavy for the quad rotor. Maybe you've got to go upstairs and things like that. And this type of, the Big Dog here, it's a possibility of doing it. And you can see it can bump into things. People can bump into it, and it's pretty robust in terms of, how it reacts and so forth. So, you've got some great opportunities there. And I'm not going to sort of go through the whole, the whole video, but I mean, it can deal with, slick surfaces. If you got an oil slick, in the plant, in fact, it might pick up on it. In fact, it may also say, hey, I found this slick surface. We need to get somebody over here to clean it up. So again, some really nice use of the data and so forth. So let's go on to, some other interesting things going on with robots. And I think, here in particular with automation, actually, this is not so much on the robotics side, but on the automation side, even, the saw, right? The table saw is probably our biggest concern about people getting hurt, right? And we see this all the time. I mean, I tell you, at the university, we really work hard at, how can we prevent this? Well, this particular saw has been, instrumented with a brake, and brakes are fairly common. But the idea is, well, how can we, prototype this thing so it actually stops and it doesn't cut a finger, right? And I'll show you how it's done in a second. But look, there's a hot dog. Now, I will say they didn't actually stick their finger in. They did use a hot dog. But, that hot dog, and here's the sort of the slow-mo, it's a capacitance sensor. But as soon as it detects that hot dog being contacted, which would serve as a finger, it backs away. Yep, a little bit of a nick, but it's there. And, what we're talking about there, again, is not so much, it's not so much that, we can do it, but we can do it very cost-effectively with something like a table saw. This is not a high-tech piece of equipment. You do need the brake on there and so forth, and it can be done. And in fact, sort of the next big push. So, yes, I mean, interacting with humans on these machines, but the next big push really is going to be with the so-called cobots, right? The robots that work with people. And right now, if you're familiar with these cobots, and them working with people and so forth, what you see is you say, well, yeah, the robot works in one area and a human works in another area, and they do not interact. You keep those two, entities separate. If a human goes in the robot area, the light cage, then the light cage shuts the robot down, because you want to, if that robot hits the human, if it can carry a 500-pound payload, and if it hits a human with a 500-pound payload, the human is in big trouble. But what we see now, is that there are some opportunities for humans and robots and automation to work together. And it is based a lot on, control and so forth. And so this is from a group over in Germany, and you can see, yeah, there's the robot, it's hitting the dummy over there and so forth. But what you can do is you can put sensing on there, and you can use vision systems and so forth to understand when a human is coming in close proximity, or in fact, if a human is in contact with the robot, and control that robot, okay? So, again, you can see here that the robot is stopping. It's bouncing off the human as opposed to the human bouncing off of the robot. Here, of course, no control. Here, control, right? And so, you see there's a little bit of an impact, but that robot backs off pretty quickly. And in fact, here's a very brave, individual basically showing you, that, you can actually hit, there's some impact on the human, but it works out well. And in fact, here's one. I'm not sure I would have done this, but he's a brave soul, and there you go. Direct impact to the head, and he's smiling in the end, so he's still happy about it. But really, we are going to see more and more humans and robots interacting, where the robot isn't good enough, but we don't want to put a human in a situation of moving really heavy payloads or doing tedious tasks. So the human will help the robot get to where it needs to be, and then the robot will complete the task. Or the robot will maybe move big, heavy equipment in, and then the human will complete the task. So it's going to be a completely different thinking on automation. And by the way, when you set up your cell, it'll be a cobot-type cell. So, and as you need more automation, you'll just ramp up the automation. You will not have to kick humans out of certain parts of the production facility and then put automation in. You'll just ramp it up. So, let me mention a little bit about additive manufacturing. And additive manufacturing really is all about building up. So we think about subtractive. If I want to machine something, if I want a hole in something, I think about drilling the hole. Additive, and we can think about it as 3D. 3D printing is a subset of additive manufacturing, but it's about building up material as opposed to taking away material. So if I want a hole, I would actually put material around an open space. It's kind of exciting because if you take a look at a hole, if I'm thinking of drilling a hole, it's going to be circular in cross-section, a constant cross-section, it's going to be straight. If I can put the material around the empty space, it doesn't need to be circular. It doesn't need to be straight. You could even put cooling channels in your engine block and things like that if you're going to build the engine block up, layer by layer. It allows you to do great geometry. Here's a hand actually holding a hollow sphere, and this hand is hydraulically powered. All the hydraulics, the whole hand, and everything was built in the same machine using additive manufacturing. So it allows you to get great geometry, all sorts of neat things. So, and again, here you can see this honeycomb shape. So in fact, that ball is a honeycomb ball, so it's very lightweight as opposed to a solid steel ball that it's holding. But you can also mix and match materials. I could put different types of materials together. Now there are, of course, compatibility issues and so forth, but we can integrate electronics, directly into our, into our designs and so forth. So we can improve on functionality. As I mentioned here, this hand is hydraulically driven. The hydraulics were built right into it. And oh, by the way, if I want to change a little bit on this hand, I just, change my CAD model. I say, print me a new one. So, I don't need to, machine out a whole, different one, or I don't need different fixtures and so forth. It's all built up together. This allows us, of course, some significant capability in terms of things like supply chain, management. So let's say you have a bracket that's holding a stereo, in a car. You may print up the bracket, and now you don't worry about stamping out hundreds of brackets ahead of time or thousands of brackets ahead of time. And if the stereo changes slightly, the vehicle changes slightly, you need a slightly different design. Instead of creating new tooling and so forth for stamping, you just change the CAD model and print up, another bracket. Now, I will say that, printing up the bracket, might cost you a few dollars, where stamping it out might, be, a few pennies, per piece. but you don't need the investment in the tooling, and your whole, inventory and so forth. So, is paying a couple of dollars for a bracket, worthwhile in terms of paying for the tooling and then amortizing it over several thousand parts and then loading it up in terms of the stamping machine, and then not being able to stamp out just one or two, but having to stamp out thousands to be cost effective, for just one run, and then storing those, right? So there are going to be some very interesting things happening, with additive. And again, it goes all back to our CAD/CAM systems. They're all digitally, all linked together and so forth. And we see, of course, even new standards, coming along and new infrastructure. We may not need these big, long supply chains, as we can produce, right at the assembly line and so forth. So these are things that, again, that we look at and that we have to understand and that are coming down the road and that we have to consider. And certainly, if I take a look at this, and these are coming out of Terry Wohler's, the Wohler's report, the U.S., in fact, actually, these are the 201, so these are from 201.2. The 201.3, the numbers are pretty much the same. There's been significant growth on the sales of the 3D printer, the left-hand bar chart. But the U.S. pretty much uses about 3/4, of the 3D printers out there. And really what we see are the 3D, the additive manufacturing, and in particular, this is the low-cost stuff. And what we see is these things allow us to be very innovative and forward-thinking and trying out new things. And this is very much, how it works, in U.S. manufacturing. But some of the things that we do worry about is, well, hey, if I can print up a part, somebody else could print that part up as well. So what happens if somebody gets, my design? That's a big question. But let's say I'm General Motors, and I have a part for my car. Well, I've got to supply that part to, my different suppliers. Let's say Pep Boy. My car has a problem, and I want to go to Pep Boy and get this part for my car. There's this whole supply chain to get this part over to Pep Boys. Well, what if GM could just say, well, you just download the file and Pep Boys, you print it up. So now we don't worry about that whole supply chain. By the way, it doesn't matter whether the car is 30, 40, 50 years old. We don't need to save all the tooling and so forth to make that part. We just have the CAD file. If you want this part, it gets downloaded. You could charge the same amount of money, so somebody's making an awful lot of profit, but you don't worry about all of the steps in between. Of course, if it's that easy to make a part, the other thing we do worry about is security and validation. So what's to say that now this turbine blade, that I'm putting in my aircraft engine, is the real thing? I mean, somebody could have just printed it up, in a forgery. So again, you have to be very careful about these things, and we have to start thinking about how do we track what we make so that what you are getting is truly a genuine part. And the other thing I really am excited about is we see a lot of these types of machines going into schools and so forth, where the kids are using them. And again, this is getting back to, our students now are coming to our, are now coming to our technicians, and they're basically saying, yes, here's my CAD/CAM file, to produce the part. So they're no longer coming with the drawings, but they're coming, with the CAM information. And that's all coming through a lot of this excitement in STEM, science, technology, engineering, and mathematics education. So I think a lot of good things are happening there, with the additive, manufacturing. And really this sort of leads into the bigger picture, the digital manufacturing. And let me just talk about the history, because a lot of people have a hard time believing that this is going to happen. But look, in the 80s, our records, and those of you who are old enough, our records, became CDs. And people said, you'll never replace my record. Well, not only replace the record, records are coming back. Yeah, but, I don't think you're going to get rid of iTunes. They're just not going to, replace iTunes. In fact, once we got compression, iTunes really worked out, and they enabled all sorts of great capabilities and new business models and so forth. And again, now the record companies are not making that many CDs, but they're just selling them directly. So is that good? Is it bad? Yes, there are IP issues and so forth, but you no longer have the supply chain that you have to deal with. You can get directly out. And the artists, they can get out on the web and they can actually establish themselves before they have to go off and try and sign a contract with the big guys. So it's quite nice. Same thing happened in two dimensions. So now we think about, pictures. It took a little bit longer because, if you want your sound, you want 10 times the resolution or the length of a sound file, well, it's just 10 times the memory and 10 times the processing power. For a 2D image, it's 10 times 10, right? Because, it's two-dimensional, so now it's 100 times. But still, the people turned around and they said, look, you'll never replace my Kodachrome. I can tell you, if you type Kodachrome into Microsoft Word today, it'll underline it in red. Kodachrome is gone. Microsoft doesn't even recognize it anymore. And in fact, back in the early 90s, if I said, name a few camera companies, you might have said, Nikon, you might have said, Olympus or Canon, you might have also said Polaroid or Kodak. Well, a couple of those companies aren't around. You certainly wouldn't have said Samsung, or Sony, and yet that's where we are today. In fact, today the biggest producer of digital cameras is Nokia. It's not even going in a camera; it's going in a phone. And that data compression, in fact, has allowed us to even go, if you want to think sort of 2.5D with time in there, we've got movies and so forth. And again, I'll just give you two words, Blockbuster and Netflix, and you can see how things can change very rapidly and how this technology can change rapidly. Well, I tell you, the same thing is going to be happening in terms of three-dimensional models. So instead of pixels, we will have voxels, and we will now represent things in terms of voxels as opposed to a lot of these, CAD files and so forth. CAD files will be digital. So if we take a look at that, the way things are going to go, just like we had here the 1D and we digitize it, and then the 2D and analog and we digitize that 2D, we will digitize our 3D volumes into these voxel models that will allow, computer processing, of the digital information, just like we do digital signal processing or digital image processing on our computers at home nowadays. We almost never do any analog processing, some special cases, but not typically. The same thing will be true for 3D. Now, the problem, of course, that we have with using this 3D type of model is it can be enormous. Think about a 1 meter by 1 meter by 1 meter, block, and you want to have a micron, so 1 part per million resolution. Well, 1 by 1 by 1, you cube it, but that's a million cube. That's 10 to the 18. That's like a petabyte of information. And to give you a feel, this chart here shows, AT&T produces 30 petabytes, process 30 petabytes a day. So we are very far off from being there, but with data compression and some of the newer technologies coming along, I think we have a good shot at it. And what are we going to be able to do? Well, we're going to be able to do things like this. So this is some work that that we had done where we had a CAD model. So this actually is an STL. It's a three-dimensional model, but it's a digital model. We've simulated that, and that's 5-axis machining. And that last part there is a 5-axis machined head, okay? And it only took us about 10 minutes. So we were orders of magnitude faster to simulate and to generate the G code for this. And basically, the only thing we're using is the graphics card in the computer. So it allows us to move things along much faster and so forth. And in fact, what we're going to see open source code and so forth coming along where a lot of this capability is just going to be out there. Hey, you want to use it? Here you go. This is an open source 5-axis simulator. So if you send over, the G code and so forth, it'll tell you exactly what you're machining. And here we see that, we're machining this impeller. And again, we're going to have more and more access to these great tools, and they're going to be just like apps, just like you would have on your iPhone or on your Android, or on your Windows-based, machine. And by the way, here we're talking about subtractive manufacturing. I want to really highlight the fact that don't count out our traditional stuff. People look at that plastic head and they say, wow, did you, print that up with your 3D printer? No, I machined it on a 5-axis machine tool. And oh, by the way, here's the aluminum version. Try and print that up on your, on your printers right now. That's a pretty difficult task. Or do you want to make it out of titanium? I can do that as well. Inconel, I can do that as well. So these types of capabilities are really going to, allow us to take, again, our traditional manufacturing, tool set and move it forward, to the level where we're going to be able to take a look at, hey, I've got to do 5-axis planning of this impeller. Well, how fast do I want it? What kind of quality do I want it? And actually, in real time, as I'm designing this thing, to say, yeah, if I wanted this kind of quality, it's going to take this long to machine, and be this, and again, if you're thinking about, roughing out with your 5-axis machine, you've got your tool overlap. Well, the smaller that overlap, the higher the precision, the smoother the surface, but the longer it takes on the machine. And so how do we trade these things off, right? Well, if I'm trying to do this trade-off, and I've got a very high high-speed simulator, well, I said, okay, well, let's try this, simulate it, in a second or less, and here's my result. And so we can iterate back and forth. The designer can play around with some of these things, just like they might play around, with much simpler parts, in current CAD systems. So you're engaging, this high-performance computing. And in fact, the real exciting thing, is where we see things going with the high-performance computing and so forth is not only just simulating it, but now, look, there are a bunch of opportunities out there in terms of, hey, I'm a machine shop, and I want a quote on parts. Well, there are probably there are tens of thousands, not hundreds of thousands of parts out there that I could quote on. But how do I do that? Well, we're going to start to see this high-performance computing, that could take a look at, how am I going to make this part and give you a solution, a pretty good solution, in a tenth of a second. So all of a sudden now I can quote on 10 parts per second, or in 10 seconds 100 parts, or in 100 seconds, so in under 2 minutes 1,000 parts. And I can go out there and I can look which parts are best suited for me and my machine, and by the way, the other way around, or what machine would I need if I wanted to capture some of this market, or if I'm a machine tool vendor, hey, what machine should I be focusing on in terms of, where the big market is, or a tooling supplier. What tool should I be using? So these models will even take a look at, here's how you would machine it, here's your tooling specifications, and by the way, I know you only have a 1/4 inch and a 1/2 inch ball mill, but if you got a 3/8 of an inch, you can actually knock off, 20% of the time. And oh, by the way, it doesn't necessarily have to be for only one machine. I can go to multiple machines, and I can reschedule my entire shop. And all of this, can be a web-based product. So, so now you can focus on the machining aspect of it, and let somebody else, take care of a lot of the higher level thinking, and provide you the tools, So really the direction that, that we're going, is we'll download these models from the internet, we'll analyze it, maybe it'll even be analyzed somewhere off on the cloud. We'll generate the path, and what you might do is you might buy the path. Maybe it's in, ACL code, maybe it's actually post-process code. And by the way, maybe the machine tool companies, will take care of this for you as a service if you buy their machine. And the tooling suppliers, if you supply them with information about how much tooling you're using, they will actually take care of your inventory control on your machine tool. People say, well, that seems pretty far out in the whole bit. Your copy machine's doing it already. Your copy machine's online. Your copy machine knows when it's going to have a problem. Your copy machine knows when it needs more toner, and it'll order it for you and take care of it for you. And you just get billed, $30, $40 a month for it. And, that's less than we're paying for our internet access and for our mobile phones, for our cell phones. So yeah, why not do it? The business models make sense. So this is it's a very exciting direction, in terms of where we're going. And again, why stop at the part? Why not take a look at your production line? Why not, why not move out, and really start to link all of your systems together? Well, they don't talk the same language. Yes, but there will be, data conversion tools that are out there that people will be able to make use of. So, in the same way that you can go off and get codecs for different, video, cameras and, video players and things like that. Will they cost you something? Maybe, but again, you're going to get what you pay for, and it's not going to be particularly expensive because, what the business model is, hey, hundreds of people will be buying this, and so if we just charge $10 a piece, well, we can make tens of thousands of dollars here. So you'll have open source that you can have access to. Even open source, well, how do you make money? Look at Red Hat, and Linux. They're doing quite well. And again, we're going to see a lot of our hardware, that's highly accessible. It's going to be repurposed. We're going to see new opportunities for the hardware that's out there, new business models for making use of that. So there's going to be a lot of interesting value added along those lines. So, again, and as I wrap this thing up, it's really about thinking in a completely new fashion. We've got a bunch of data out there. They're already out there. How can we make money off of those data? I'm showing you this part here. This is a part, I think it's an Airbus part. You see it quite often out there. My colleague, again, Terry Wohlers, handed this one off to me. The part on the top is made with subtractive, with machining. The part on the bottom, it's actually made with additive manufacturing. You remember when I said we're going to drill a hole? Well, those holes and the countersinks, those are circular, those are straight. The holes on the bottom part are not, because you don't need to make them that way. So you've got to be thinking differently, and we've got to leverage, our next generation engineers and technicians and students differently. That F-35 over there, if we continue to go the path we are, the next combat aircraft is going to take 35 years to go from initial design to deployment. It's going to be like, the old days of building a cathedral. We can't afford it. We've got to think differently. Whether it's something like, additive manufacturing that you see in that, in the third picture there, or, and again, I tell you additive, how can we make, instead of using machining, how can we do additive manufacturing? I don't think you want to substitute additive for machining, because we've been working on machining for 200, 300 years, one could argue. We're very good at it, right? But what can't we do with machining that we should be targeting additive? So these are the things that we should be looking at, and I think that are going to be very, very exciting. So In terms of wrapping it up, really, sort of the global well-being. There's my friend, the KUKA Titan robot. That puppy is going to be with us, for the future. It's going to take away the nasty jobs, that people don't want to do, and it's going to allow the United States to really leverage its highly educated and talented workforce, to move forward. And I think that the future is very rosy for manufacturing. But it is about wealth creation. We cannot be only a service economy. It is sustainable, and, by the way, it's going to be very, very efficient. And the more efficient you can be, even though energy is low cost here, the less energy you can use, the better. We are going to enable not just the big players, but the small and medium-sized enterprises. We have to do that. They have to move along those areas. It's important for the national economy. It's also important for the nation's security. And really, the United States is in a leadership role in manufacturing. We are arguably either the largest or the second largest, manufacturing economy in the world, and we need to stay there. And we see some great innovations that are allowing us to move in that direction. So for the United States of America, it is about innovation and innovation in manufacturing, and that's what some of these new tools, robotics, automation, are allowing us to do. And in fact, I do want to say this, it also is important for the world and the international well-being. Because if you look at it, and if you have manufacturing globally, manufacturing provides good jobs, it helps the economy and so forth, and people that have good jobs with healthy economies, they are much happier, and they're much, less likely to cause difficulties globally. So this also is a very important thing to remember. And I'll just close it with this final statement from Eric Hoffer, and he lived back in the 20th century. In times of change, learners inherit the earth, while the learned find themselves beautifully equipped to deal with a world that no longer exists. So the bottom line there, and I think this is very, very important, is we have got to focus on lifelong learning. You're in the workforce for 50 years now. If you stop learning when you join the workforce, you're a dinosaur even in 10 years. So in fact, the pace of technological acceleration is it's accelerating. It's becoming more rapid. And this statement is going to become even more and more important. We've got to keep our workforce up to speed, so they can use these tools, they can understand the benefits of these tools, and we also need to understand how the workforce capabilities are changing so that we can leverage their capabilities as much as possible. And I think with that, I will close it up and be happy to answer any questions that you might have.
Hello, this is Pat Wozniak again. Tom, thank you very much. It looks like we may be running a little long here, and that's okay. But if you can't stay, the entire webinar will be available for replay at 7 p.m. Eastern Time today. We have received some questions, and it would be nice to get to all of them before our time is up. Tom, here's one. Would the new systems be able to give you final machine sizes before the part is removed from the machine?
Yes. So the new systems, and again, if you're, could be that you're probing, in the machine. It will be able to give you the final part size. In fact, one of the things it'll do is be able to probe, get the part size, and actually take a look at what your tooling offsets might be, how they might need to change for the next part, or you might actually probe in terms of, roughing, and then go back and, finish things up, based on the part size. So definitely that is the case. And again, here we're talking about probing in the machine, but there are all sorts of other options. Could be scanning, with the articulated arms, CMMs, and so forth, that could be very useful as well.
Hey, Tom, would you say automation is really for production processes, and can it benefit a job shop type environment?
Yeah, so I think automation. Yes, certainly for production, but I think in terms of a job shop environment, I think it really does make sense. And again, you have to use it wisely, and it has to be done appropriately. But even is it the best use of your programmers, or your operators, or your setup person's time, to be loading, a part in the machine when a robot, might load it, or it might be automatically loaded, and so forth. That's one area. But even in terms of scheduling your machines, wouldn't it be interesting if and we see this all the time. Hey, somebody needs a part really quickly. Well, can I fit it into my machine, right? Well, you say, hey, if we could simulate which machine could do it, what tooling do we need? Yep, we have all of this types of information. That's all automation. And then, yes, let's just reschedule things. So even automating, some of the scheduling processes and so forth. So, And I think that it's becoming more and more realistic. If you go out, there are certain robots that are out there that are much easier to program, and they work with people and so forth. So I would say the answer is yes, and it just depends on to the degree that a shop can make use of it. But automation is becoming much more flexible. I think the combination of flexibility and that automation really gives you some serious capability. But you need to know how to use it. So that's where the educational aspect comes in. And these kids are awesome in terms of what we're putting out from our community colleges and our technical colleges and our universities. They're just great in terms of being able to use the technology.
Tom, here's another. Has
Sure.
anyone experimented with 3D printing of assemblies?
Yes, and that's one of the things, you'll see, oh, well, we can print anything up. We could even print up a car. Well, we're not quite there in printing up a car. And by the way, if you print a car up in your office, the big question is how do you get it out the door? But on the actual assemblies, I mean, what happens, and there are, I'm sure you could go off and Google, and you'll see that, they've printed up bearings, ball bearings, for example, fully assembled ball bearings. Now, what happens is, you've got to have some support structure because those bearings have to be built. The balls have to be built separate, from the tracks, and there will be a little bit of a connection, a little bit of almost like a little toothpick, if you will, that has to be broken off. So you've got to support it somehow, and you've got to break that off and clean that up. But the full assembly is there, but it's not just print me up a bearing and I'm ready to insert it into my car or into my tractor or something like that. So it's there. It's not quite as magical, if you will, as a lot of people have been led to believe. There is some post-processing that has to go on there. But, nonetheless, you can make functioning assemblies.
Tom, here's another one. Are our students prepared for a career in manufacturing? Basically, they are not working on cars and TVs like they were in the 50s, 60s, and 70s, and even up into the 80s.
Well, and I think that's a great question. So, I grew up in a machine shop, and this is what I did. My car today doesn't even have a dipstick, right? So, not only you can't even work on it, you can't even check the oil. You go to the screen and check the oil. And I think what we need to do is I think we've gotten past what I would say is kind of this low point, where the students really were lacking capabilities and things like that. They still aren't going off and machining and fixing TVs. We don't even have, we don't have tube testers over, in the drugstore anymore. We don't have tubes, right? The TV breaks, you don't even get the repairman in, right? You just go buy a new one. That being said, I think that there is hope, and we see the students moving forward in these directions where they are getting, this maker movement, where they're getting these, sort of low-cost, $300-400, 3D printers and so forth. So they are designing parts. A variety of different companies have their CAD packages online, free versions that students can use. They're kind of watered down, but again, they're smart. They're trying to get the students used to the CAD package so they buy the full version when they go off, to work. But they can draw their part up. They can build it up. And like I said, my technician today, a student who doesn't really have much manufacturing experience still knows how to draw it up, how to analyze it, and then how to generate the G-code with a CAM package. So it's not the same student as 30 years ago. Don't get me wrong. It's a different student, and that, we really need to retune our processes, our thinking processes and our needs and, how we're moving to the student of today. But I'll tell you what, I think that a kid that can walk up, you can say, here's my part, and they can generate the G-code using a CAM system is a pretty big step of the way moving forward. Yep, they can't run a manual lathe. They can't set up threading, operations on the lathe, but they can program these, CAM systems, and they can actually get that G-code. So pluses, minuses, we've got to leverage their new capabilities. They're thinking differently today.
Tom, how is additive manufacturing different from rapid prototyping processes such as stereolithography, laminated object manufacturing, and the like?
Well, so I think people. So they're basically the same, right? So it's gone from initially back in the 80s, like with stereolithography and so forth. That is layered manufacturing. It's additive. You're adding things on, but it was called rapid prototyping because it built prototypes. And they typically weren't functional and so forth. The new terminology is now additive manufacturing because much of what we manufacture is no longer a prototype. It's a functioning part. So they wanted to get away from that. Now, in many instances, it's not a functioning part. I'll tell you that right off the bat. That bearing that I talked about in terms of, we could use additive manufacturing to make a bearing. You probably wouldn't want to put that in your jet engine, at this point in time. And if you could put one of those in a jet engine, it would probably cost you a whole lot more than, making it with the traditional approaches. That being said, so rapid prototyping has now moved, over to being called additive manufacturing. Still making a lot of prototypes quickly, so it still can be considered rapid prototyping, but really, that's what rapid prototyping has grown up into. Sort of like NC is now, has become, CNC, right?
Tom, how does this great technology level the playing field of the future and offset the trend toward offshore manufacturing for lower costs?
Well, look, so here's the bottom line. Automation really allows you to get stuff done without as much labor, and in particular, sort of the low-cost labor, that doesn't require a lot of, high-end skill. And people will say, well, gosh, then it's going to take away jobs. You see my friend the KUKA up there. Yes, plant that I worked with, they put 320 of those in, and a number of people, a lot of them were reassigned. Some of them, did lose their, positions and so forth. The reassigned people, they program these. These are much better jobs. They're higher-paying jobs. They're programming. They're maintaining them, and so forth. And by the way, that plant became so efficient that they doubled the size of the plant. So yes, they lost maybe 100 jobs, but 2 years later they gained 3,000 jobs. So, and the U.S. is a great place, in terms of building things. If automation, so why don't other countries automate? Well, first of all, when that KUKA robot breaks, who is going to fix it? Here in the U.S., we have the people who can fix it and so forth. Who's going to be smart enough to think about how do we really use that automation, right? So there are a lot of great advantages here in the United States, that other countries, don't have. And frankly speaking, there are many instances. If you go to Honda's facility, let's say in Bangalore, you don't see thousands of people assembling a Honda. There's a lot of automation to that, and so for the higher end products, yes, you've got to go with the automation, and that really gives us the capability and so forth. Of course, automation also uses energy. Energy is relatively low cost, in the country, and the automation, in robotics and so forth requires some innovative thinking. And, I can tell you, worldwide, the United States, our culture is really touted for its innovative thinking. So this is, again, something that I think we really leverage here, and we'll see it coming back. We'll see this coming back, and we already see it coming back. And it's not even like coming back. It's not that we've really lost it. It's just other places of the world have grown up, but the U.S. is still a major manufacturer.
Tom, with the prevalence of hacking, what kinds of security measures are being taken, especially to protect intellectual property data stored in cloud-based systems?
Well, and I think that this is, and I think this is actually a very relevant concern. Both how you're going to protect your data and your IP and so forth, and also, how are you going to protect your machines? If they're all online, these robots are online, your machine tools are online, people, hacking in. And I think that there is a lot of work, very similar efforts going on, let's say with the smart grid, for our electrical, networks and so forth. Certainly we see the same thing, happening in banking. I can be, halfway around the world, stick my bank card in, withdraw some money in some foreign currency, and it'll actually tell me what my balance is. So, yes, there are significant concerns there. We will have to focus on that cybersecurity, and this is a big focus area for a number of companies as well as for the federal government. And, we'll have some issues, things will get hacked and broken into, and we see this happening all the time. No, I shouldn't say all the time, but in the various, sectors. On the other hand, if you take a look at how, places like the banking industry and the grid are working and so forth, it's a pretty good track record, and we continue to improve on it, leveraging those. So it is a concern. It's something that we're very good at and that we're getting better at, and it's something that we already have some great examples of where you can be very successful in protecting your data, protecting your IP, and then also protecting your infrastructure and equipment.
Tom, one of our audience members asked if you can send us a PDF file of this excellent presentation. I absolutely have no problem with that. In fact, I will leave it to my colleagues at the Society of Manufacturing Engineers to take care of that. However you want to do that is fine by me. Great. Unfortunately, our time is up. All unanswered questions will be passed along to Thomas, and you can expect a reply via email. The entire webinar will be available for replay. As Tom proved with his presentation, software technology touches all aspects of manufacturing, from CAD/CAM designers to engineers to workers on the shop floor. To help keep you abreast of the latest in technology and techniques, SME and Manufacturing Engineering Media have a host of ways by which you can keep in touch with the latest software and automation technologies, including the August issue of Manufacturing Engineering included a special software supplement available for download at the URL you'll see on the screen. The September issue includes a feature article on ERP software, and the October issue includes a feature on shop floor data management. Every issue of Manufacturing Engineering includes a software update section and our password Q&A interview with software industry experts. Thank you for joining us for this Manufacturing Engineering Media webinar. We hope you found it informative.